Okay. So in the last video, we talked about the concept of an antiderivative and finding antiderivatives using indefinite integrals. And then we kind of went over some techniques for evaluating those. So let's take a look at a few examples. Okay, we want to find the most general antiderivative of the following functions. F prime of x is equal to x to the 10th power. G prime of x is equal to x squared minus 5x plus 2. H prime of x is equal to 5 over x, and so on and so forth. Why are these things including these prime symbols? Well, they didn't need to, but it's kind of a reminder that antiderivatives are functions whose derivative is this thing. So if I'm given f prime of x, then its antiderivative is just f. Okay? Now, this one is a power function, x to the 10th, and the rule for that was to add 1 to the exponent, which would be 11, and then multiply by the reciprocal of that number, which is 1 over 11. And that's all there is to it, to that one, okay? So if you are, when you're first getting used to doing antiderivatives, it's a good idea to always check your answer by taking the derivative of this and seeing if you get what you started with. And that's pretty easy to verify here. I did forget one thing though. It says find the most general antiderivative, and this is only one antiderivative. I have to include that plus c to show that I'm giving the most general antiderivative. Let's do another one. G prime of x equals x squared minus 5x plus 2. So here, if I want to find the antiderivative of this thing, notice on its own, it doesn't exactly match any of these specific rules here, right? But it does include a combination of those rules. So I see power function right here, x to the x squared. Okay, I see a function that has this form to it, something of the form, well, actually it's this down here, constant multiple, so k times a function of x. Here it looks like -5 times x, and then I have a constant function. We had a rule for that as well. And I'm combining them with addition and subtraction, which we had a rule for as well. So if you want to take the antiderivative of a sum or difference of functions, you just take the antiderivative of each one independently and then add or subtract the results depending on what operation was used here. So basically what that means, if I think of this as a function that has 3 terms, I can take the antiderivative of each term independently and just keep the minuses and pluses where they are. So here's what that would look like. Antiderivative for x squared, I add 1 to the exponent, which is 3. Then I multiply by the reciprocal of that number, minus 5x. So I'm still going to have a minus. And then 5x. So think of that as x to the first power and use that power rule on it. Add 1 to the exponent, x squared now, and then multiply by the reciprocal of that number, 1/2. There was already a 5 there, so 5 times 1/2 is 5/2. Okay, plus 2. Remember the rule for constants, if you want an antiderivative of a constant, it's just that same constant times x, 2x. And then as always, we put a plus c here. Once again, it's a good idea to take the derivative of this to see if what you get is the function that you started with. And I'll let you verify that. It's pretty straightforward. You could probably do that in your head. But to keep us moving, h prime of x equals 5 over x. So h prime of x, we've written it that way, but it's the same thing as 5 times 1 over x. And you don't have to rewrite it this way, but if you're kind of, feeling a little rusty on some of these algebraic concepts, it might be helpful to put it in this form, because now we're looking at it as a constant times a function, and this function 1 over x, we know what its antiderivative is. So this implies that h of x is equal to what? Well, the constant multiple rule says that if you have a constant times a function, The antiderivative is just that same constant times the antiderivative of that function. So that would be 5 times the natural log of the absolute value of x. Remember, now we want to use absolute values. And then you still need this plus c here. Okay? D, this last one here, I have j prime of x. So that means we're looking for j of x. We want the antiderivative of this. So for this, I have a combination of two exponential functions that I'm subtracting. Here, 3 to the power of x. Remember, if you took the derivative of this, you would get the exact same function, but then you'd be multiplying it by the natural log of the base, natural log of 3. I want to do the opposite. I want to divide by that. So this is going to be equal to 1 over the natural log of 3 times 3 to the power of x minus, and then over here, I have a constant times a function. So its antiderivative is that same constant times the antiderivative of e to the x. But e to the x is its own antiderivative. And so I still end up with a 4e to the x there. But then I also have to include this plus c. Okay? Fairly straightforward, but you have to practice this a little bit so that you don't default to taking derivatives. We're doing the opposite of that now. We're taking antiderivatives. All right, this next example is essentially the same idea as the previous one, except for a couple of things. One, we're going to be using that indefinite integral symbol. Remember, it means the same thing as what we did in the previous example. It means find the most general antiderivative of the function in your integrand. But the other thing about this is the functions are slightly more complicated looking, and all that means for us is that we have to do a little bit of algebraic work on some of them to make it a little more clear what the anti-differentiation technique is. So let's start with this one. For A, I'm taking the antiderivative of 3x minus 1 quantity squared. If this were a derivative problem, if I were taking the derivative of this, I would have a couple of options. Probably the best option would be to use the chain rule, okay? Because the chain rule says that if you have a composite function, we have a rule for how to take the derivative of those, and it's fairly straightforward in cases like this. But this is an antiderivative, and we haven't talked about what the antiderivative version of the chain rule would be. Now, there is a thing that's kind of like the chain rule in reverse, and we are going to talk about it, but we're just not there yet. So at this point, we need to approach this in a different way. And the most straightforward way would be to actually square this out. Expand it. So if I square 3x minus 1, that's 9x squared minus 6x plus 1. Okay? Now at this step, I can use some of those rules that we've talked about. And I'm not going to do this for every problem that involves this, but I am going to do it once. I'm going to show, kind of using those anti-differentiation techniques, how this thing would split up into 3 integrals instead of just 1, because I can do an integral for each one of these terms. So first of all, I can take the indefinite integral of 9x squared, and that 9, because it's a constant multiple, can be pulled out. So I can write that as 9 times the indefinite integral of x squared dx. And then I have that rule that tells me how to deal with, sums and differences of functions. I can split it up into, I have a difference here, a difference of this integral with this integral. Once again, I have a 6x, I can pull the 6 out. I have the integral of just x dx there. And then finally, I have this plus, and I have a 1, the integral of 1 dx, which oftentimes we'll just denote dx. The 1 is implied there. So I can now evaluate this kind of term by term. So the antiderivative of x squared using my power rule would be 1/3 x cubed. But 1/3 is going to get multiplied to this 9 here. So it's actually 3x cubed. Okay? Now here, the antiderivative of x, remember, think of that as x to the first power, would be 1/2 x squared. But that 1/2 is going to get multiplied to that 6, and I get negative, I almost wrote 1/2, negative 3x squared. Finally, there's this integral of dx. Remember, that's really technically a 1, so it's a constant, and the antiderivative of a constant is that same constant times x. 1 times x, which I would just write as x. Then we have plus c. So that is my indefinite integral. Okay? So notice that, again, what we had to do here was expand that function by squaring it, and then handle this term by term. And again, I actually wrote this as like a sum and difference of indefinite integrals where the constants have been pulled out. But generally speaking, I'm not going to do that every time. In fact, this is the only time I'm going to write all of that out, because you can do these antiderivatives kind of just by looking at each term and thinking through what it would be. You don't have to show all of this every time. Okay, just wanted to do that once. Okay, for part B, I want the indefinite integral of the cube root of x dx. Now, if you go back to that list of integration rules, we didn't talk about how to take antiderivatives of radicals, but that's because we don't really need to. We don't need an extra rule for that. Remember, the cube root of x is the same thing as x to the 1/3 power. And that power rule applies to every power function, x to any power, except for the number -1, which we talked about that as a special case. And by any power, I mean even non-integer powers like 1/3. So let's think through what this would look like. I have to add 1 to my exponent. 1 plus 1/3 is 4/3. And then I multiply by the reciprocal of that exponent, which would be 3/4. Then I just have plus c. And that's it. That's the whole thing. I'm not going to bother rewriting this in radical form. I'm just going to leave it as a rational exponent. That's preferable here. Okay? All right. Part C, I can do something very similar, because notice I can write this 7 over x to the 5th as 7x to the -5th. And we really want to do that because that's, again, showing us that we can use the power rule here. So what would that look like? Again, I'm going to I have this 7 out here already. I'm just going to remember that I have that. But then I have a -5. I want to add 1 to that. -5 plus 1 is -4. Then I want to multiply by the reciprocal of that -4, which is -1/4. There was already a 7 out front, so that makes this -7/4. And then we've got plus c. Okay? And again, I'm not going to worry about converting this back into some other form. I'm not going to write this x to the -4th as a 1 over x to the 4th. It's fine to leave it in the form of a power function. Okay? Finally, part D. This is the most complicated looking example of these 4 up here. We have 6x to the 4th minus 4x squared plus 9 all over 5x squared dx. Now, at first glance, when you look at that, you might think, okay, I need some kind of like reverse rule for the quotient rule, because this function is in the form of a quotient. And for derivatives, we have the quotient rule for dealing with stuff like this. However, this is not a derivative. It's an antiderivative. So we can't just go in and apply the quotient rule, which is a derivative rule. In fact, we don't need to come up with any kind of reverse quotient rule to handle this. Instead, we can simplify it. Because I have a numerator that's made up of 3 terms and a denominator that's made up of 1 term, I can split this up into 3 individual terms. 6x to the 4th over 5x squared minus 4x squared over 5x squared plus 9 over 5x squared dx. Okay, at this point, hopefully you can see why this is the same thing as this. Notice the common denominator. So if you wanted to add all this back into one big rational expression, you keep that denominator the same, 5x squared, but then you add the 3 numerators, or subtract if you have subtraction going on. You would get back to this if you did that. Now that I have individual terms, I can simplify them all independently. So I have 6/5 here. X to the 4th over x squared is just x squared. I have minus 4/5 here. X squared over x squared is 1, so the x squareds cancel out. And then I have plus 9/5. And then that x squared in the denominator, I can rewrite as just x to the negative 2nd power like this. Okay? Now this is in a form that's much more easily integrated. So here, if I want to integrate this function, I would add 1 to the exponent, which is x cubed, and then multiply by 1/3. But multiplying this by 1/3 would give me 2/5. Here, I have a constant. Constants are easy when you take antiderivatives of those. You just put an x in front. Here, I need to add 1 to the exponent, so I'm going to get x to the negative 1 power. Then I multiply by that, the reciprocal of this, which is still negative 1. All that does is it changes this plus to a minus. So I get negative 9/5 x to the negative 1 plus c, because you need that constant of integration in there. And that's it. Again, you don't need to try to find a way to combine all of these back into one big rational expression like the integrand that we started with. Just leave it the way that it is. That's going to be much easier than trying to give yourself more work to do. Okay? All right. So the next thing I want to look at here is what to do if we're being asked not for the most general antiderivative of a function, but more specifically a particular or a specific antiderivative. Because in a lot of cases, even though we have infinitely many antiderivatives to choose from, we might want to narrow it down to just one that describes the situation that we're talking about. So in order to do that, you need more than just the function whose antiderivative you're looking for. You need additional information about that function, which will usually come in the form of f of some value equals some other value, which is given to you. In other cases, which we'll look at, sometimes we're given the value of the second derivative of our function, or something additional like that. So let me do one example. We'll look at another example probably in part 3, but we'll do at least this one here. So it says find f of x if f prime of x is equal to 8x cubed minus 12x squared plus 13, and f of negative 1 is equal to 18. So in order to get f of x from f prime, we need to take its antiderivative. That's how you undo a derivative. So f of x would be equal to the antiderivative of f prime, which looks like this, 8x cubed minus 12x squared plus 13 dx. And by this point, we've done several of these, so we can kind of move through it a little bit quicker. Add 1 to the exponent, x to the 4th, multiply by the reciprocal, which is 1/4. 8 times 1/4 is just 2. Again, minus, add 1 to the exponent, so I get x cubed. Negative 12 times 1/3, because I'm multiplying by 1/3, would just be 1/4. Or sorry, by 4, not 1/4. Plus 13x. That's what happens to constants. And then we have plus c. Okay, so this is right now the most general antiderivative because of that plus c. If I want to get a specific antiderivative, then I need to figure out the exact value of c that needs to go here so that this information is correct. Okay, so we're saying that this is what f of x is equal to. Now let's plug in negative 1 and set that equal to 18. So 18 is equal to, plug negative 1 in here, 2 times negative 1 to the 4th power minus 4 times negative 1 cubed plus 13 times negative 1 plus c. Okay, let's work this out. So negative 1 to the fourth power is 1 times 2, that would be 2. Negative 1 cubed is negative 1 times negative 4 is positive 4. And then this would become minus 13 plus c. So 18 is equal to that. 2 plus 4 is 6. Minus 13 would be negative 7. So I have negative 7 plus c. Add 7 to both sides. C is equal to 25. So what I'm going to do is take that, put that in for the c here, and that's going to be my answer. F of x is equal to 2x to the fourth minus 4x cubed plus 13x plus 25. Okay, so again, just to recap on that, your very first step is to find the most general antiderivative, which is going to give you some function plus a constant of integration. Then use this. These are oftentimes called initial conditions. So you can use your initial condition by plugging that x value into the function you just found and setting it equal to that output. And then that creates an equation that you can solve for c. Okay, so we'll see some more like this, but that's going to be in part 3.